Good day, everyone. Joel Legacy live. I think this is working. Let me flip screens. Here we are. All right. So here I am again, just random, saying hello to everyone on a Sunday afternoon, 1:45 p.m. here. We've been getting a lot of storms all night, actually, and we've been losing the electric on and off all day, so don't mind me if I just disappear in the middle of a chat here, probably because my internet goes down. But other than that, it's been pretty quiet Sunday around here. So just doing my typical introduction and waiting to see if anybody is around on a Sunday afternoon, which there might not be very many people around, which is fine because these lives all get archived and people can watch them later. But yeah, so with that said, again, hello. Just trying to get some seconds to pass here. 1 minute, 1 minute I've been live, and here are some people. Hello, Chief. I'm actually paying attention to the chat. See. So yeah. So hello again, everyone. And what was I talking? Yeah. Hi Z seems to be the thing everybody's asking about, which is kind of weird because it just randomly came up, but I guess it's something that people should know about in a high Z coil. So hello everyone. Yeah. So I've been talking about that in the last few lives and showing demonstrations with the high voltage transformers, and everyone was like, oh my god, you can do that? You can limit current without using a resistor? Well, yeah, through a high Z loop, you can do that. And very similar results actually as if you're just looking for pure potential and limiting the current, the PEG cells were doing that. I was using the PEG cell, here's one here. And they work good for limiting the current and giving you a potential difference. And what's nice about it is because they have a DC potential, you can stack them up, right? So you build the DC potential and you use them as a limiter at the same time. But they help kick in with the pure potential. But if you're just looking for pure clever way of bringing having a high resistance without actually using a quote-unquote resistor, a high Z loop is a potential way to do that. So I was measuring it in other videos and showing you that like at even 20 volts, if we short it out, like the loop through a high Z, we only draw 1 milliamp, which is very good. And it hardly does anything to the actual voltage. I showed with the voltmeter over here that we were getting like 19 volts when it was putting out 20. So it's a good way to keep the potential without collapsing the dipole for whatever project you might have in mind in Tom Bearden terminology, right? And on the side here with my new space, I've been trying to get my scope working. Couldn't find the power adapter, but I think I found it here. It's very handy to have. And I think this is it right here. There's a USB one. Hopefully it's the right one. Goes into the power input. So that fits, so that's a good sign. Hopefully I didn't fry it. There's a USB power. We shall see, because I really want to get to using this. And it gives me 1 foot of wire. That's really practical, isn't it? Oh, these engineers from overseas, I tell you. Just to keep it appropriate, right? Oh, that still doesn't even do it. Ay, ay, ay. That's ironic. They give you like 1 feet of wire. see if that'll do it. It's all the way over here. Oh my goodness. We got it, I think. Might not have enough power on that thing. It's not enough power. My goodness. Let's try this one here. I really want to have the scope back and running. Oh, I think this one's good. Well, this little one didn't have enough power to draw it. Ah! And we're back in business. Just gonna get these dishes out of the way. Awesome. Let's see if that really works. It works. It's getting the test signal, no problem. Ah, well, that's a relief, right? Good to know. Yeah, for those who's wondering, since I've moved to like the new space here for my private experimenting, I lost the power adapter for my scope, and I knew it was USB, but the other end was a normal power input. So I've been fighting for about a week to try and find any darn. Worst came to worst, I was just going to like build one myself if I had to, but preferably I would like to use the stock cable that came with it. So that's good that it's working like that. So hello everyone who's just coming in on the live chat here. Just random Sunday afternoon. And I finally got the scope working, so that's great. Is it normal for the metal in the back of the scope to get all bent up? I don't think it would be. Unless you're up to something, right? See, my new one here is all plastic, right? Quote unquote made in China. The old one is all metal. Very solid, but I gotta clean it up. The buttons don't really respond anymore. That's a job to take the front plate apart, and gotta get the solution to clean up all these contacts. But other than that, the old one works great. Just gotta get motivated to clean it up one day. So where were we? High Z loops. Yes. So I wanted to show the high Z loop here again. So now that everyone can see it here, high voltage transformer on the high voltage side, high Z, which is the high resistance. So I'm feeding DC here. Power supply is set to 10 volts. So I've got an LED here just to show you that it actually works. But I don't think you're going to see it lighting up from the camera here. So what I'm thinking of doing is just placing it nicely over here. Connecting that. Since the camera can't. So I think I'm going to take the iPad and take a close-up picture of that, where you can see that it's on. There we go. With the right angle. Take a picture. All right, and then show you guys picture up close. That, I don't know if I've got the right angle here. I'll see it in a moment if you can see that. That's right now the LED lighting up through the high Z loop. So that's why it doesn't like burn out, because it's got like less than an MA, but it lights up because it basically likes the potential, right? So it's lighting up just fine. Now, what's interesting is, again, the draw here. If you can see that, is 0 MA, 10 volt 0 MA, so maybe half an MA through the high Z loop. And what's nice about this is it's not what you'd expect, where in a typical resistor, it'll eat up a lot of it in heat. And even as a dead short, if it's a low resistor, which takes up a lot of current, right? Now what's going on here is there's basically no heat on the high Z side, and it's not like it's that the power supply has to work like 100 MA or 200 MA through this, and all we're getting is 1 MA that's left. Meanwhile, the power supply is still working very hard. No, it actually limits your input sink, so you're not siphoning. If this was a charged 10 volt capacitor, for example, we'd be taking less than 1 MA through the high Z loop to maintain this LED, right? So now what comes interesting with this, see, I actually have a scope on this power supply, which I haven't figured out how to use yet, but it has a scope because it's a repair tools power supply. It's a bench tool. But what's interesting here, if you want to start crudely getting into the Don Smith kind of thing, if you want to start pulse width modulating the core here, you get some interesting effects on the DC side of the high Z loop. So if I were to crudely do this, you're not going to probably see that through the camera here, but if I drive the low Z side with like a 9 volt battery, I'll do it manually, pulse width modulation. What you get there is very nice blinks. And for temporary, we somewhat, because we're energizing the magnetic flux of the core, we're bringing down the impedance a little bit. So for a moment, it draws like 2 milliamps from the power supply, but you're getting the advantage of pulse width modulation, like Bedini would say. So what's interesting here is I get the very high voltage kickback here. You could actually see the spark. That's Bedini's inductive kickback. But that inductive kickback is saturating the core. So on the DC side, it helps contribute to a nice bright pulse. Now, whichever you'd want to automate that through a switch or a natural source, an electrostatic displacement, the environment, another pickup antenna, if it's the environment, you're getting that effect for free now. So that's probably enough to make a lot of you think a bit of what that can do to your potential well over here if we introduce pulse width modulation on the what you would consider the primary side of the circuit. This could work with AC, by the way, as long as you're like an audio amplifiers, the frequency modulated is a lot higher, so you can get away. An audio magnetic amplifier, essentially. But we could use the same principles in electricity. Works very well, actually. So, you know, in very crude, easy to understand demonstration, right? I'm not making any claims you're gonna power your house this way, but it makes you think of a system you'd want to design, build along these principles and concepts, right? So there's a lot to learn. It's a lot of fun. And Bedini said it, you know, and it starts resembling Tesla's impulse technology when you start modulating. So Tesla was onto it himself in his own ways. He used spark gaps, so did Don Smith. But that is the core effect, right? You're modulating a DC or static potential. So, yeah, very interesting stuff, and I'm glad if it helps. I don't know if you actually saw that light flashing there when I did it manually, but it does. So clever ways of trying to get every efficiency out of every system, right? So I'm noticing everyone is having a good times with the comments. That's pretty cool. I'm happy everyone's getting along. And I'm happy my scope is working. That's the thing. And that's another thing. I could hook it up on another demonstration, but when you do pulse width modulation, you can see it floating across your DC if you would scope that. So you can sort of shape your DC, so to speak, or a slower frequency. Yeah, lots of fun here. But the problem is, if you're going to do this with AC, you got some interference unless you put a second, an identical, an easy fix is an identical transformer in series. Primary will filter out whatever's going on AC on this from the secondary side, right, from your pulse width, because you don't want your pulse width modulator to get fried. You know what I'm trying to say, from the standard transformer action, right? But you could filter that out, literally nullify it with a second transformer identical in series. So you can still drive it, but your primary circuit, I did it really quick, it didn't matter here because it's just a battery. But if you were to have a really elaborate switching here, you'd get the feedback from what's going on this side. So an easy way to eliminate that is an identical transformer, you know, phase canceling essentially. So that makes it safe for the drive control circuit. So yeah, this is Sunday afternoon with Joel. So just thought I'd say hi like I usually do and elaborate. I should shut this off, it's still running here. Elaborate a little bit of what you can do with high Z loops, and then what happens when you start pulse width modulating them on the other side. So one can take all of those concepts and build something pretty neat. Take the inductive kickback from the pulse width modulator, store it in the capacitor. I don't know, so many. I did a lot of things too in the past. If you look at all the old videos of different configurations, it's a lot of fun. Yeah. How did I learn all of the high Z stuff? Well, uh, I guess Tesla coils in the way. Maybe not as high Z, but here's something what you consider high Q. You can inherently make it high Z as well. Now that's for another day. If you start playing around with resonance, high Q and high Z, you get some very interesting effects. Now you can transfer the energy much more efficiently from point A to point B. True. What I'm getting at is you can dump the core completely if you got high frequency, high Q, high Z. Don't need the core no more. That's what Don Smith was up to. It's a pure resonant magnetic energy coupling effect. So the high Q will give you the high volts, high potential resonance. It will build up a very strong field. So, and the high Z makes it so you don't have to pay a lot to trigger that high Q state. So you start working with high Z, high Q systems, integrating them, you realize you don't need that core no more. And you're no longer linear, you're non-linear. So you get very interesting effects when you start playing with non-linear interactions. your your secondary and primary is no longer linear coupled if there's no core. So you can let the high Q resonance do its thing, right? And all the pickup coils become more like antennas, like a radio station kind of effect. So, yeah, a lot of stuff to digest, that's for sure. Definitely. You start playing with one thing and you're like, oh my goodness, I can start really fine-tuning all this stuff, right? Then once you get resonance and you amplify your field, you get a very, very strong field. Then you're able to introduce very, very strong what they call displacement currents between capacitor plates. You put coils nearby, that triggers the same movement a coil would see through magnetic flux in a core, but you don't actually have the core. You're feeding it more directly this way. So very interesting effects indeed. And Don Smith in his own ways, you know, everyone has their way of trying to explain it, I guess, right? So, wow, yeah, lots of stuff here. A lot of experiments I still want to try, and there's so many pathways, right? It's all about crossing energy domains and letting the resonance build up in its energy domain and trying not to feed it back if you can. Use the byproduct from another domain. It's pretty simple stuff. Well, simple, quote unquote. Tell the traditional engineer that, right? They don't like to admit that we can, even in a closed loop, for example. I don't know if I can draw it with my iPad here. Do I even have a draw? Maybe I should get one. Like a paint or something. Sketch pad or. But yeah, I mean, I'll try and show you this right here. These engineers have a hard time understanding. This is a battery. I put a LED and a resistor and send them back. That's a closed loop. Well, the first thing they say is you're never going to get more on the output side than what you put in the input side. If you do measure, which we have, more energy, then you're doing something wrong or your metering is wrong. They don't want to understand, what if I continue the loop and I put a solar panel here on the side, I continue the loop, I put a windmill here on the side, then I feed my loop, but the battery is just part of the. So now you have 3 units coming in. Of course, I'm going to get more energy on the output without breaking any laws of physics. Why can't we all just sit down and say it's not wrong to have a circuit, if it's designed through antennas and rectifiers and whatever, to pick up other units of energy and apply it in the loop? And yeah, of course we're getting more energy, but we're not saying the energy comes from magic hocus pocus. We're just using additional global sinks. Instead of a windmill, if I want to build an antenna system instead and get the static displacement and interference and earth currents, why can't I do that? If at a certain point it all starts working, it's just an example of yes, we're taking external energy. And they look at it and they won't even realize or even conclude that, yeah, we can, and we do it all the time, by the way, in power systems and power plants that feed the grid. A little bit of wind from over here, a little bit of solar from over here, a little bit of coal. That's at the end of the day, once it's all converted and transduced to the same kind of power in the right phase, you just inject it in the grid, right? I mean, why am I not allowed to do the same thing in small? Yeah, I have this battery. I need more than what this battery can supply, but I'm going to tap into external energy sources that are free to me. No, not free energy in the sense it comes from nothing, just that I paid for this battery, but I didn't have to pay for the wind. I didn't have to pay for the sun. I didn't have to pay for the vibrations in the city that drove my piezoelectric capacitor plates or whatever it is crazy I want to design. You can go on and on and on, add all your external energy systems in that loop, and essentially you're going to have a closed loop, but that's what drives your final load. You keep the closed loop for your final load, you know? The same way as displacement current will induce a new EMF in its own closed loop, but it won't interfere the source. So yeah, I mean, so much, but it's just the perspective needs to change a little bit. You know, they accept it in one way, but then in the other, when you're trying to do it in small, like let's say an audio amplifier that has the concept of tapping into multiple energy sinks, they'll tell you it violates the laws of physics. The power company does it. Why can't I do it? The power company, I got a video, goes as far as asynchronous condensers at the power plant to recycle the S apparent power back to real power, like we talk about with reactive gains and everything. They quietly do it for their own systems and inject the power back. They put it back in phase. Right there, at depending on the design, some advanced designs have it. And it's okay. It's funny because it's okay. It's okay when they do it, but when somebody else proposes a similar recycling mechanism for a household item or whatever, impossible, breaking the laws of physics. You can't do that. Only we can do that. Shh. You know, it's funny, but it's not. Ay, ay, ay. Ah, well, I don't want to get too carried away here. Yep. So, wow. With that said, it was a good session, and I think I've pretty well proven, what I wanted to show you. The LED can run on pure potential through a high Z loop, and if you want to do something interesting with that, you can pulse width modulate it, and you essentially got yourself a magnetic amplifier. And it does work with DC. I mean, um, yeah, in a way where it decreases the resistance a little bit through the core saturation. In this configuration here, because I've got a core here, ideally I'd build my own high Q, high Z system like I talked about, but just for the sake of demonstration, I use what I had and try and explain what was going on within its context, right? Because the core does something in this essence here. So with that said, I will wrap it up and say goodbye for now, and I hope you all join me on my next video. And again, thank you all for watching and your support and your conversations and everything. Thank you all.